a larger example of the use of the A-star algorithm. I'll start with an undirected graph. Now, of course, this is actually a directed graph if we have arrows in both directions on each edge. So this weighted graph has a start node S and an end node T, and we're trying to find the cheapest or shortest path from S to T. And the whole idea of the A-star algorithm is that we don't have to visit every node. Now, we start with a structure which is a min heap, where the key for the min heap is the red number, which is the estimate. And for S, the start node, the true distance from S to S is 0. The heuristic is 27, so the estimate, the sum of those two, is 27. And that's the smallest value here. And so this node is then deleted from the min queue, and its out neighbors are pushed on. Here is what the structure looks like after one step. We deleted S, and so I drew a vertical line through that item. In the array, for each node, we have the name of the node, the actual true minimum cost that we have found so far between S and that node, which is of course initially 0, then followed by the heuristic value, which is green, which is given to us in advance by some person or something that generates it, and then the estimate, which is the sum of those two. And the last row in the array is the back pointer. So for each of the 6 new nodes in there, the back pointer is S, the start node. Now, this particular picture diagram shows the structure after 2 steps. In the second step, we deleted the node which had the smallest value of the heuristic of the estimate, which is 28. And then we inserted all of the out neighbors of 28 where except for the ones that we already have. So we inserted R and X. And on their rows, we give the true cost from S to R or from S to X, together with the heuristics of those two, together with the estimate, which turns out to both be 29. This diagram shows the state of the structure after 3 steps. Now, we deleted all the nodes which have the estimate of 29, which is the next smallest number. And those nodes were C, R, and X. And then we inserted the new nodes that we could obtain from them, which are O, J, and E. And again, we fill in the 3 rows, well, the 5 rows, actually, the name of the node, O, J, E, and at the bottom, the back pointer, and then the value, the heuristic, and the estimate. Here is the structure after 4 steps. We deleted all the nodes that have 29 as their estimate. No, we already did that on the previous slide. We're deleting all the ones whose estimate is 30, and those elements are Z and J. And then we insert the new nodes that we get from them by out edges, and those are E and A.
Hold on. Action.
Okay, after 5 steps, our structure, we have deleted the nodes A and O and L. And we have inserted the nodes W, I, and Y, which we obtained from them. Now you notice we're getting closer and closer to the goal, which is T, but we have failed to visit F, M, V, and H at all. This is intentional. This picture shows what happens after 2 more steps. I didn't show the intermediate picture because we only lost 1 node there when we deleted Y, and then when we deleted W, we got no additional nodes. So basically, we've deleted Y, W, and E, and O, and we get B and Q. Actually, I think O was deleted the previous step. But in any case, we now have finished, we now continue to build the table in this direction, toward the right. This is our last figure. Let's point out something. The red structure is a tree. We could call that the optimal path tree, because it shows an optimal path to a lot of the nodes, but not all of them, because we never get to H, V, M, and F. And finally, we have reached T, which is the goal. And so you can see how we filled in the additional entries here. The whole idea of this algorithm is that we don't visit all the nodes. This example, being kind of skinny and to the left and right, actually does use most of the nodes here. Try to imagine, though, that this could be part of a much larger graph with nodes all up and down and around, in which case the A-star algorithm might only visit a small fraction of all the nodes, thus saving time.